So in our last lecture, we learned that there is something called as Lagrangian of a system, which is subtraction of kinetic energy and the potential energy. We also learned about the equation of motion in 1D. So what was the equation of motion in 1D? It is d by dt, so rate of change of time, which is first one is the total derivative, and then we have a partial derivative. Remember, first one is the total derivative, and inside the bracket we have a partial derivative with respect to x dot. And x dot is what? It's nothing but velocity minus again the partial derivative of the Lagrangian with respect to the coordinate. When I say with respect to the coordinate x, it means we are dealing with all things that move in only one dimension. We consider all the examples in 1D. We consider spring mass system in 1D. We consider free falling object in 1D. We consider a freely moving body in 1D. Now let us consider cases in 2 dimensions. What will be the cases in 2 dimensions? So whenever I consider 2 dimensions, it means I must take an x-axis and I take a y-axis. Agreed? So let me label them. So this is say my y-axis and this is say my x-axis. If an object say is moving along this direction with a velocity v, okay, a ball is moving in this direction with a velocity v. You know that the velocity v will have 2 components. One in the x direction, we have already discussed this in our last lecture, so dxi, and one in the other direction, that is the y direction, dy. So we have 2 dimensions. Similarly, if you calculate the kinetic energy is what? Half into m into v square. Okay, so for this object, the kinetic energy will be half. So the kinetic energy will have 2 terms. One will be the kinetic energy with respect to the x-axis of velocity, that is vx square, and another is the kinetic energy with respect to the y-axis velocity, that is vy square. So that is half okay, so 2 kinetic energy. Hence, so there are 2 coordinates. One is the y coordinate and another is the x coordinate. So now the Lagrangian equation of motion will take a small twist. There will be 2 Lagrangian equation of motion, one for the x coordinate and another for the y. So for the x coordinate, the Lagrangian equation of motion will be as usual. We have already written this. So this will be the x coordinate of the equation. Okay. And then there will be another Lagrangian equation of motion for the y coordinate. So for the y coordinate, we have everything same, just that there will be a change in x. So the x will become y. So this is partial derivative of del L with respect to y dot. Y dot is the velocity in the y direction minus del L divided by del y. This equals to 0. Agreed? Now you would say that, okay, so what to do now? Let's see what to do now. As I've mentioned earlier, that we are considering a freely moving object. So this object is moving freely along this direction with a velocity v. Now tell me, what is the force law for this freely moving body? The force in the x-axis of this object is 0, agreed? Hence, and the force in the y-axis of this object is 0. Or I can say the total force vector, which is a combination of force fx and fy, is 0. I mean total force vector. So what is total force vector? Total force vector will be composed of a force in the x direction, that is fxi, and we know that fx is 0 for a freely moving body, and a force in the y direction, fyj, and we know that for a freely moving body, fyj is 0. Now Lagrangian will give you the, as I said, Lagrangian will tell you what are the forces. Okay. So in the x-axis, if you put the value of Lagrangian, now you will ask me what is the Lagrangian. In this case, the Lagrangian is kinetic energy minus potential. Since this is a freely moving body, so potential energy is 0, we'll have only kinetic energy. So what is the Lagrangian? The Lagrangian is the total kinetic energy. So the Lagrangian is made up of the kinetic energy in the x direction, that is Vx square, and then the kinetic energy in y direction, Vy. Agreed? This is the Lagrangian of a freely moving body. Now if you put the value of L in the first equation, then you find that there will be a equation at the end which says that f of x will be 0. And if you put it in the second equation, you will find that f of y equals to 0. Okay, so the Lagrangian equation motion says that a freely moving object in 2D will have forces in the x and the y axis as 0. So let me evaluate for the x-axis so that you don't face any problem. So how to evaluate? So d by dt of, now tell me one thing, del L by del x dot. So as I said earlier, what is x dot? X dot is velocity in the x-axis. So what should I write? So I should write del L divided by del. So x dot is velocity in the x-axis. So I should write del v of x minus del L by del x. I am evaluating the first one. Okay. Now, if you put the value of Lagrangian, just tell me one thing. What will happen to the quantity inside the bracket? Since the Lagrangian has to be done, since there is a derivative with respect to velocity in the x direction, so the partial derivative will act only on this part. This part will be 0 because there is no partial derivative with respect to Vy. When you do partial derivative with respect to first part, what you get? You get m into Vx. And since the Lagrangian is independent of coordinate, the second part is 0, that equals to 0. Now tell me, what will be the next expression? M. What is d by dt of Vx? d by dt of Vx is acceleration in x direction, that is 0. What is max? Max is the force in the x direction, that is 0. So Lagrangian equation of motion happily tells you that for a freely moving body in 2 dimensions, the force in the x-axis and the force in the y-axis is 0. Okay. Similarly, in 3D, what you need to do? In 3D, you need to add one more coordinate, that is z, and write the entire Lagrangian equation of motion in terms of z. So I hope you can do this yourself. Now, I'll tell you very interesting thing. Let me rub all this. So I hope you have noted this. Okay. So you see one thing, that in this 2D, this ball has the degree of freedom to move either in x or in y. So what is the minimum degree of freedom for an object in 2D? The degree of freedom is, so degree of freedom is written as DOF. So DOF means degree of freedom. Degree of freedom means in how many directions it has freedom to move. In 2D, it has only direction to move in 2 directions. So that degree of freedom is 2. If the degree of freedom is 2, then you need then the minimum number of coordinates to represent the object will also be 2. The minimum number of coordinates to represent the object will also be 2. Now you say, what are we doing? What are we doing this? Why are we doing this? The reason is, consider a pendulum. You know that the motion of a pendulum is 2D. Will you agree on this? Because the pendulum will go here, and then here, and then here. Now why I said the pendulum has only 2 degrees of freedom? Because you see, either the pendulum can go forward or the pendulum can go up. Okay, because of this the pendulum is moving. So what is the degree of freedom for a pendulum? If the pendulum can move either in x or in y direction, so number of degree of freedom is 2. Now to represent the pendulum's motion, how many coordinates do you require? So if you take this motion of a pendulum and evaluate it using only x coordinate and y coordinate. So you can evaluate the entire motion of the pendulum. So take this as origin, and you can use the x and y coordinate to represent the entire position of pendulum during the motion. All the positions of the pendulum during the motion can be represented by only x and y. So what is the minimum number of coordinates to represent the motion of pendulum? The minimum number of coordinates to represent the motion of pendulum is 2. Now you would say, what is the big deal? What's the big deal? It is quite logical. We can see the minimum number of coordinates is either x and y. There is no motion of the pendulum in the z direction. It doesn't matter. Yes, it matters, and it's very important. The reason is, when I say that the minimum number of coordinates is equal to degree of freedom, when I say minimum number of coordinates, I don't mean only the Cartesian coordinates. I mean the minimum number of coordinates required to describe the pendulum in any coordinate system is 2. If I ask you how many polar coordinates do I need to represent the motion of the pendulum, then you can directly tell me without looking at anything. You can say that since the degree of freedom is 2, the number of coordinates is 2, so the number of polar coordinates should also be 2. And that is true. We need only 2 polar coordinates r and theta to represent the motion of pendulum. You see, describing the motion of pendulum in Cartesian coordinate is difficult. Why it is difficult? Because the motion is very much weird when you look at the entire motion of the pendulum in Cartesian coordinate. So somebody said that, hey, let us not study the pendulum system in Cartesian coordinate. Let us study the pendulum system in polar coordinate. And he said that when the pendulum moves in the other direction, there are 2 things that you need to know. One is r, the length of the pendulum, and another is theta. If you know r and if you know theta, then you can exactly tell where the pendulum is. What is coordinate system? Coordinate system means you use the coordinate system to depict the position of objects. So in pendulum case, either you use x and y to tell where the pendulum is, which is very complicated, or you use the polar coordinate system to study the pendulum. Now, when you are studying the pendulum, when you are studying the pendulum in polar coordinate system, then you need to have the Lagrangian in the polar coordinate system. Agreed? The question is how to write the Lagrangian. So we have 2 coordinates r and theta. So there will be a Lagrangian in r, and there will be a Lagrangian equation of motion in theta. Easy? So write the same equation in r. So there will be a Lagrangian equation of motion d by dt of del L by del r dot. Remember, there is always a dot of coordinate. Del r dot minus del L by del r. So this is the first equation of motion. And the second equation of motion will be in theta. So there will be d by dt of del L by del theta dot. Remember, there is a dot always. Del theta dot minus del L divided by del theta equals to 0. Now you would say, okay, so you have written Lagrangian equation of motion. What's the big deal? Can you find something concrete by using this Lagrangian equation of motion? I'd say yes, we can find something concrete. How? So first you need to know what will be the equation for the energy and the potential energy. Okay. So you need to find 2 things. You need to find the kinetic energy of the pendulum. You need to find the potential energy of the pendulum. So let us find the kinetic energy first. So we know that the pendulum always moves with a velocity v, and that velocity v is tangential to its orbit. And we know that v can be written as r omega from the circular motion. We know that. Okay. So what is r omega? R omega is nothing but r. So what is omega? Omega is theta dot. It is rate of change of angular displacement. So what is the kinetic energy of the pendulum? So kinetic energy is very easy. You know that kinetic energy is half m into v square. V is the linear velocity. And you can write this in terms of omega and theta dot. So the entire term now we need to calculate the potential energy of the pendulum. How to calculate the potential energy of pendulum? So let me draw the diagram of pendulum again. So if you look at the pendulum, when the pendulum is here, and say when the pendulum is about here, then when the pendulum is here, consider this is the place where the potential energy is zero. This is the place where the potential energy is zero. When the pendulum rises by a distance, say the pendulum rises by a particular distance h, then what is the potential energy at this part? The potential energy mgh. Very easy. Okay. But now, what is h? We know that if this is theta, then this entire length is r, and this length will be what? This length will be r sin theta. So this length will be r cos theta. R cos theta. That is the projection of r. Okay, so projection of this length. So again, let's show you the projection of this length on this part will be r cos theta. So what is h in terms of r? So h is actually total r minus r cos theta. Quite simple. Okay. So this is your h. So what is the potential energy then? What is the potential energy in case of a pendulum? So let me write it down. So we know that potential energy mgh, but since here h is r minus r cos theta, so the potential energy in case of pendulum is mg r minus r cos theta. Okay. Now that we know the potential energy and now that we know the kinetic energy, we can easily write the Lagrangian. We can put the Lagrangian into the equation of motion, and we can find the equation that governs the motion of pendulum. So let us start. So we have two Lagrangian equation of motion, one in r and one in theta. Okay, remember that. Now you know what is your Lagrangian is. Now you know that your Lagrangian is half, so the kinetic energy is half m r square theta dot square. This is your kinetic energy, and you have to do minus the potential energy. What the potential is m g. Take the r common, you get 1 minus cos theta. This is your potential energy. Can I simplify it a bit? So let us simplify this a bit. So this will be half m r square theta dot square minus, so that will be plus m g r cos theta, and what will be the last term? The last term will be a minus m g r. Now let us put this Lagrangian into the second equation. Let us see what happens when we put the Lagrangian into the second equation. So can you tell me what will be the value of dl by d theta dot? You see, only the first term is a function of theta dot. Rest all are function of theta. So we'll have m r square theta dot. Agreed? So this will be del L by del theta. And now, what will be d by dt of this? So we have the first term as d by dt of del L by del theta dot. Okay. So since the theta is a function of time, why? Because theta is changing with time. The angle of the pendulum with the original is changing with time. R is constant. So the d by dt will act on theta dot, and you will get what? You will get theta double dot. Then the second term is what? The partial derivative with respect to. So the second term is the partial derivative of L with respect to coordinate theta. So can you tell me what happens? The first term will be 0, last term will be 0. So what is this term? This term will be m g r sin theta. mgr sin theta. But we know that when cos goes to sin, there is a minus sign. So now what to do? Now put these values into the equation of motion. Okay. So let us see what do we get. So what are we doing? We are going to write this equation. So the first term is m r square theta double dot. Agreed? This is my first term in the Lagrangian. What is my second term? My second term is minus of mgr. So there will be plus. So there will be mgr sin theta. We know that for small angles, sin theta can be approximated to theta. Okay. So what is the equation now? We get m r square theta double dot plus m g r theta equals to 0. I hope you remember what is this equation. This is the simple harmonic equation for the pendulum. So there will be theta double dot plus g by r theta equals to 0. So this is the SHM equation, the simple harmonic motion equation for a pendulum. We have already studied this in our oscillation chapter, and we know that omega square is nothing but g by r. Okay. So and so what is omega? So omega is root over of g by r. So what is time period? You know how omega is linked with time period. So what is the time period of the pendulum? The time period of the pendulum is 2 pi root over of L by G. So what is the conclusion of this discussion? The conclusion of this discussion is that when you have an object that can move only in 2D, it means the number of coordinates required to describe the object is only 2. Whether you describe it in Cartesian or polar coordinate or cylindrical coordinate, you always need 2 coordinates. The Lagrangian and the Lagrangian equation of motion depends on the coordinates. If you use the polar coordinate to describe the system, then your Lagrangian equation of motion has to be written in terms of polar coordinate. All you have to do is replace the x part in the part 1 by r, and the second part will be by theta. And then this is how you do it. Also, when you are describing a system in polar coordinate, you also need to keep in mind that the Lagrangian, that what is Lagrangian? It is kinetic energy minus potential energy. So when you are describing a particular system in polar coordinate system, even the kinetic energy and the potential energy both should be written in terms of polar coordinates. Only then you can have your Lagrangian in polar coordinate, and then you put the Lagrangian into this Lagrangian equation of motion. So I hope you have a clear understanding of how to work with Lagrangian in 1D, in 2D. Okay? In the next lecture, we'll talk more on this advanced classical mechanics, and we will use this Lagrangian formulation to study even the central force motion. That will be in the next